All right, so let's start with the final chapter of this power electronics course, which is on AC to AC converters, also known as AC voltage controller or a AC regulator. So we'll be starting with some basics and then we will study the single phase voltage controller. So AC voltage controller basically is a converter which converts AC into AC and controls the voltage, the current, and the average power, which needs to be delivered at the AC load supplied from the AC source. So as we have already discussed in previous lectures, the conversion from AC into AC is done using electronic switches. So the combination of switching, which is connected in between AC source and a AC load, actually helps us to have a regulated output at the load. Okay, so if we want to have a regulated AC supply at the load, when a circuit or a system is supplied using AC signal at the source, which can be seen from here, the AC voltage source is connected to a converter, which in turn is connected to the load. So now this regulation at the load, which is AC, is done using these two switches. So the arrangement of these two switches, which are thyristors in this particular case. So these thyristors or SCRs, the arrangement of these S1 and S2 makes this circuit possible to have a current in either directions in the load, in both the directions, you can say. So the combination of these two switches, S1 and S2, are in parallel to each other. Like this S1, the anode is connected to the source, while cathode is connected to the load. While on the other side, the switch S2, the anode is connected to the load and cathode is connected to the source. But both of these switches are connected in parallel, but in opposite direction. So in that case, we can call this connection as an anti-parallel or inverse parallel connection, where the current is carried on opposite directions in both the switches. So this will be the voltage across these two switches. And the load current IO is flowing through this load, where we have a voltage which is denoted by VO, which is the load or output voltage. So going further, let's say this voltage source has a sinusoidal voltage supply connected to this converter, as we can see from figure 1 of this waveforms. So voltage Vs is a sinusoidal supply input. VO is the output voltage at the load. Since these two switches are SCRs, so we have some firing angle for these two switches. So let's say in the positive half cycle, switch S1 is conducting and it starts to conduct after an angle alpha. So from 0 to alpha, we do not have any conduction of a SCR, switch S1. So in that case, the voltage, the source voltage Vs is now applied across the switch, which is VSW. So this will be the voltage across the switch, VSW. So when neither of the switches is conducting. So this Vs will be equal to V switch, VSW, which will be applied across the switch S1. And at angle alpha, switch S1 starts to conduct. So now this supply voltage is now received at the output. So we can see from here, at angle alpha, switch S1 triggers, and now we have a output voltage same as supply voltage till it reaches angle pi, half cycle. Now at angle pi, the negative half cycle starts. And in this negative half cycle, now switch S2 will need to be conducting. So this S2 starts to conduct after angle alpha, as denoted here with angle pi plus alpha. So pi is the angle where negative half cycle starts. Alpha is the firing angle where switch S2 starts to conduct. And as soon as the switch S2 starts to conduct, the supply voltage is now received at the load voltage, as we can see from here. And then the cycle continues. So in positive half cycle, we have a positive half cycle received at the load depending upon the firing angle alpha of switch S1. And in the negative half cycle is received at the load depending upon the firing angle alpha for the switch S2. And then the complete process continues every cycle. So this angle, this figure 3 shows us that when this switch is off, we have a supply voltage applied across the switch itself, which is VSW. So it means the output voltage alternates after every half cycle, and the value depends exactly on the angle alpha. So based on that, we can easily say that this principle of operation is quite similar to the controlled half-wave at the load in the positive half cycle, and in the negative half cycle it was completely clipped. And in this case, we'll see the observations in the next slide, so we'll see the difference. But before going into the observations, we'll just see that the load current, it contains both positive and negative half cycles, as we have seen here in this case. So this is the load voltage, and the load current follows the load voltage, alternating after every half cycle. So in positive half cycle it is positive, in negative half cycle it is negative, and so on. So we can still say that this is identical to the controlled half-wave rectifier, but using symmetry, the results can be extrapolated to describe the operation for the entire period. We'll see that. So based on that, we have some basic observations. Observation 1, the switches SCRs cannot conduct simultaneously. Either S1 is conducting or S2 is conducting. Both are not conducting simultaneously, not at the same time. So in positive half cycle, switch S1 is conducting. In negative half cycle, switch S2 is conducting. So they cannot conduct simultaneously. Observation 2, the load voltage is same as the source voltage. We have seen that in previous case. When either of these switches is on, either of the SCR is on, the load voltage is 0 when both the SCRs are off. We have seen that in previous waveforms. The switch voltage VSW is 0 when either SCR is on and is equal to the source voltage when neither is on. The average the average current in the source and the load is 0 if the SCRs are on for equal time intervals. So if SCR1 is on for a particular time period in positive half cycle, and SCR2 is also on for the particular same time period in negative half cycle, then we can say that the load current, especially source as well as load current, they are zero, because the average comes out to be zero. So the average current in each SCR is not zero because of the unidirectional SCR current. But in each SCR, in each switch, the average current is not zero. Collectively, it is zero in the circuit, but in individual SCR, it is not zero. That is also an observation based on the waveforms in previous slide. So the RMS current in each SCR is 1 divided by root 2 times, as we have done in rectifier's case, the analysis. The RMS load current if SCRs are on for equal time intervals. And as we have already discussed, that S1 conducts in the positive half cycle, means when it is triggered at angle alpha, similar to the half wave rectifier. Where the circuit differs from this is when the source is in negative half cycle. So the only difference between half wave rectifier and this AC to AC voltage converter, the only difference is that in the negative half cycle, we have some voltage across the load, which we could not have in half wave rectifier. Just by applying a gate pulse or a firing angle at S2 in the negative half cycle. So that makes a difference compared to the half wave rectifier. So in that case, we can say that we can calculate the algebraic output of the voltage and current. Something like this. So the output RMS voltage for half cycle, we take a root mean square for each half cycle, starting from alpha till half cycle pi. This will be the voltage applied, Vm sin omega t, which is the supply voltage, taking square and under root, taking mean divided by pi and then under root. It comes out to be this value. So for alpha equal to 0, the load voltage is a sinusoid. Exactly the same RMS as we have at the source. So the load RMS and source RMS are same. So as per the plots or the waveforms, the normalized voltage and normalized current, this is the normalized voltage, and the normalized current at the load, if we have a resistive load, is the RMS voltage calculated divided by the resistive load. And the power factor, we can have this active power divided by the apparent power. And after simplifying, we can have the expression of this. So the power factor is dependent upon the firing angle alpha. And the average source current is 0 because of half wave symmetry. We already know that. But the average SCR current is not 0 because every half cycle, each SCR is drawing some current, which is having some average value, which is from alpha to pi, because at alpha, the conduction of the SCR starts till angle pi. And this is the source voltage, Vm sin omega t, divided by the load, integrated for an angle 2 pi. So we have an equation 5.6, similar to the current we saw in half wave rectifier. So each SCR carries 1/2 of the line current. So the RMS current in each SCR can be divided by root 2. So this is the waveform, or you can say the graph, which shows that if we keep on increasing the firing angle, the RMS output voltage keeps on decreasing. That we have already seen in previous circuits also. So at angle 0, it is as good as a diode circuit. So we can have a maximum voltage at the output. And if we want to decrease the output voltage for regulation, we can change the firing angle or we can increase the firing angle. So these graph shows the harmonic content, variation of harmonic content depending upon the firing angle, delay angle alpha. So this is for the fundamental component. As we increase the firing angle, the harmonic amplitude goes on decreasing. And for the third harmonic also, it goes on decreasing after some angle alpha, and so on. So firing angle alpha also has an impact on the harmonic analysis, as we can see from the graph in this slide. So this is just a basic example. A single phase AC voltage controller, as we saw in the previous figure, has this voltage as a supply. The load voltage, the load resistance is 15 ohms. So we want to find the delay angle or the firing angle, which needs to deliver a 500 watt to the load. And then find out the RMS source current, and then the RMS and average current in the SCRs, and the power factor, the total harmonic distortion of the source current. Okay, so the required RMS voltage to deliver 500 watt to a load of 15 ohms, just using the expressions of voltage, current, and power as we have analyzed in the previous slides, we can use those expressions to find out the power, the active power, and the output voltage, because active power given is 500 volts. And rearranging this equation, we can easily get the output RMS voltage as we want to get that. The RMS voltage is 86.6 volts, and putting this into the equation of 5.4, we can easily get a firing angle of 88 degrees. So putting that in equation 4, 5.4, sorry, equation this one. So putting this equation here, we can calculate the angle, firing angle alpha. And this RMS current can be easily found out from equation 5.4. This one. Similarly, we can find out other parameters as well. So now, हेलो हेलो, हाँ जी, हाँ जी, हाँ जी, बोलिए बोलिए, बस ठीक है, आप सुनाओ। 2002 में